and we'll start today with box plots and outliers. So hopefully you remember studying and using box plots back in GCSE and through the transition course before you started A-level maths. But a quick reminder of the anatomy of a box plot. A box plot represents a data set, and we have indicators, we have markers that split that data set into 4 sections. Now these sections are not equal in width, but they are equal in frequency. So 25% of the data exists here. 25% exists in between these 2 points. Another 25%. And then finally the top 25%. So the box plot shows markers for the median of the data, the point which has 50% above and 50% below, and the quartiles of the data, the points which have 25% below, 25% above. Technically, each of these markers we can give some notation to. Q0 is the minimum value represented in the box plot. Q1 is the lower quartile, Q2 is the median, Q3 for the upper quartile, and Q4 is going to be the maximum value. So a box plot can actually show us quite a lot around the spread or the shape of the distribution that we're working with. Okay, some additional things that we can get straight away from a box plot include the range. We know the range of values because it will be the maximum value minus the minimum value. Q4 minus Q0. And maybe more interestingly, we have the interquartile range, which is the range between the upper quartile and the lower quartile. Q3 minus Q1. Well, that should just about cover what you studied at GCSE when it came to box plots. And we just want to extend this. We want to go a little bit further. We can be a bit more specific about what is happening with box plots. Hopefully you know already by now, from our studies around measures of location and spread, that there's a specific reason why we like to use the interquartile range as a preference to the range. And the reason is that there may be extreme values in our data, and the range would be affected by those extreme values. The maximum, the minimum, they would themselves be an extreme value. And if we try to calculate the range using an extreme value, we get what might be an unreliable result. The interquartile range is not affected by these extreme values. We weren't interested in the maximum or the minimum, so we've safely navigated away from using extreme values when it comes to the interquartile range. Now, understanding what to do when we have extreme values and how to mitigate the statistics that we work with when we have extreme values is an underlying theme throughout the whole of the course. So always keep that in your mind. What if there were extreme values? Do I have an alternative? Do I have a contingency? Well, with that said, extreme values, if they affect the range, they would also affect the box plot that we produce, since we have an indication for the maximum and the minimum. So what can we do in this case? Okay, firstly, let's try and define what we will consider an extreme value. Well, let's actually start with the interquartile range. So this is the gap between the upper quartile and the lower quartile. This is the middle 50% of the data. Well, we use this as a measuring tool, and we decide that actually, let's take one interquartile range either side of 50%. And we could say anything within this limit, we would say that that was acceptable. Anything outside is an outlier. But we take it even further. We want an extra level of certainty, an extra level of caution before we determine something to be an outlier. So we don't just say one interquartile range above the upper quartile. We say 1.5 interquartile ranges above the upper quartile, 1.5 interquartile ranges below the lower quartile. So we've been quite liberal here. We've been quite lenient that anything that falls within these limits, anything that falls within this region, we'll accept it as a valid piece of data. But anything beyond that, we will consider it to be an outlier. Okay, so I've represented this graphically, and you can see spatially the allowance that we're given for the acceptance region, the allowance that we're given before we consider something to be an outlier. And let's actually have a look at an example of how we would calculate this, even if we weren't working with box plots. So in this specific question, we've been given 15 pieces of data. I've ordered them myself. You won't always be given them in order. And we've been asked to identify the outliers. So the first thing I'm going to do is I'm going to try and find the quartiles. I know the position of the lower quartile I can find by using n plus 1 over 4. And that tells me that the fourth value is my lower quartile. Fourth value you can see is 34. Similar thing for the upper quartile. This is going to be 3 times n plus 1 over 4. So basically 3 times the fourth position, which tells me it's the 12th position. I can count all the way along, and I realize the 12th position is 41. This is my lower and my upper quartile. From them, I can calculate the interquartile range. Interquartile range is the difference between them. The difference between them is 7. That box in the middle of the box plot would have a width of 7. And I can go ahead and find 1.5 times the interquartile range, which is 10.5. So my outlier boundaries will be any values that are 10.5 above 41 or 10.5 below 34. Okay, so 34 subtract 10.5 gives 23.5. And if we just check at the top end, 10.5 added on to 41 gives us 51.5. Okay, so from here, let's just look at the original data again. Is there anything above 51.5 in the data? There isn't. Is there anything below 23.5? Yes, there is. There's one number below 23.5. There's one number outside of this acceptance range that we've calculated. 13 is an outlier. And our first step is just being able to identify whether or not we have outliers through this calculation. Now, typically, we're going to use 1.5 times the interquartile range, or by default, that's what we should be using. An exam question or a practice question that you come across may well redefine what you should use as the definition for an outlier. It may ask for an outlier to be 2 interquartile ranges away from those quartiles. It may ask for it to be just 1. But if it hasn't redefined, the default is 1.5 interquartile ranges. Okay, well, this is a measure of outliers that uses the quartiles. There is a second measure or a second definition of outliers which says an outlier is anything beyond x bar plus or minus 2 standard deviations. So it's up to you to choose between the two of these. Usually the question would have led you towards the fact that you've already calculated standard deviation and the mean to go ahead and use that version, or if you've already calculated the quartiles, you should be using the 1.5 times interquartile range version. But both of those are available for you to use. So let's revisit this earlier question, and from here I can calculate x bar and sigma, all from this original data. And if I put that into the formula, x bar plus or minus 2 standard deviations, we get limits for our acceptance region, which are quite similar. I've got 22.0643 as the lower limit of acceptance and 51.4023 as the upper limit of acceptance. Anything beyond these would have been an outlier. And once again, even with this new definition, 13 is still an outlier. So in this question, we've actually been given the raw data, so the lengths of 12 giant African land snails, and we've been given some summary statistics just to help us on our way. So we're initially asked to find the mean and the standard deviation. So just using the summary statistics as they're presented, x bar, sum of x over n, gives us 21, and sigma It's going to be the square root of sum of x squared over n minus the sum of x over n, all squared. And we get 3.8297 for the standard deviation. We had options here. We could have put it into our calculator and got those results, but remember, whenever you have summary statistics alone, we have to go the long way round. We have to use the formula to calculate these statistics. And the examiner is going to design opportunities for you to do both in the exam, to use your calculator and to show you're aware of the formula. Okay, substituting these values in to our x bar plus or minus 2 standard deviations, we get limits of 13.34 and 28.66 to 2 decimal places. And we can identify that the only outlier we have is 32.5. Okay, so 2 ways that we should be able to calculate and identify outliers from a list of data. Both of these are necessary, both of these will be assessed, both of these need to be committed to memory. These will not be in the formula book for the exam. You will have to memorize these. 1.5 interquartile ranges above the upper quartile, or 1.5 interquartile ranges below the lower quartile would be an outlier. So this is basically 1.5 interquartile ranges away from the box of the box and whisker plot. And additionally, we could identify an outlier with anything that is beyond x bar plus or minus 2 standard deviations. In both of them, we've identified a way to talk about the middle. We either looked at the box, the middle 50% of the data, or we looked at x bar, the mean, which is a measure of central tendency, a measure that shows us where the middle of the data is. And then we created a buffer zone, an acceptance zone around that measure of the middle. So we either had the 1.5 interquartile ranges as our buffer, or we had 2 standard deviations as our buffer. But both of these have the same underlying concept for us to identify and specify outliers. Okay, and we're just about finished, but before you move on to some practice questions, let's take a quick look at the specification and exactly what it is that students are expected to be able to show, exactly what the examiners are anticipating you will be confident on. While you read through that, I want to quickly remind you that it will be sensible for you to come back and watch this video at a later date, maybe come back in 2 or 3 weeks or before an assessment. And as you watch through the second time round, because you've done your practice, a lot of what you go through here should resonate with you much more. And you have a chance to really embed your understanding of the difficult concepts, the ones that have been flagged up as A star.